Now we're going to jump into 7.2. It says sample proportions for categorical variables. And the first topic is the sampling distribution of p hat. Okay. So again, what does that mean? If we looked at all possible samples of a set size, okay, and then we plotted them, that would give us the sampling distribution. So all of these are different p hats if we line them up. Okay, ranging from 0 to 1, possibly. So the mean, the center, okay, would be denoted like this. The mean of the sampling distribution, that's what that represents, is going to be equal to the true proportion. Mu of p hat would equal rho. And in particular, this distribution, okay, since p hats are all over, it has a certain spread or a certain standard deviation. Okay, so the standard deviation of the sampling distribution of a sample proportion, okay, so sigma of p hat, or the spread of p hat, how the p hats are spread out, we can find that by this equation. Okay, so we would take the square root of rho times 1 minus rho all over n. Okay. And it says, note, the 10% condition must be satisfied, so the population has to be at least 10 times larger than the sample. So for instance, if we had a sample of 100 people in some capacity, for this formula to be valid, all right, the population size would have to be at least 1,000. Because this is 10 times more than this. All right, if that's not true, then this formula doesn't necessarily work. Okay, so that's called the 10% condition. Okay, and sometimes it's called the independence condition. Okay. All right. So the next sentence says, as n increases, as your sample size increases, the sampling distribution of p hat, that's this thing, okay, by plotting all our p hats out there, it becomes approximately normal. It says before you perform normal calculations, we need to check that the large counts condition is satisfied. And the large counts condition says that n times rho has to be greater than 10, and also that n times the quantity of 1 minus rho has to be greater than or equal to 10. So let's look at an example to see how these numbers work. It says about 75% of young adult internet users ages 18 to 29 watch online videos. Suppose that a sample survey contacts a SRS, which stands for a simple random sample of 1,000 young adult internet users, and calculates the proportion. Okay, that's a sample, so this would be p hat, okay, who watch online videos. So they told me that's the true proportion, the true population proportion. So that right there is rho. So rho equals 0.75 there. Okay, this right here, it's a sample of size 1,000. Okay, so part A, it says, what is the mean of the sampling distribution of p hat? So they're asking for mu of p hat. Well, based on this definition up here, the mean of the sampling distribution of p hat is going to equal rho. And what did we get in the question? We were told that rho was 0.75. Okay. Part B. It says find the standard deviation, or the spread, of the sampling distribution of p hat. So they're asking me for sigma of p hat. Okay. They're asking me how the p hats are spread out. We're going to use this formula for that. Okay. So I'm going to take square root of rho times 1 minus rho all over n. Okay. Again, this is part B. All right. So I would take 0.75 times 0.25 all over 1,000 and put it in under a square root. We can do that on one step in the calculator. Okay. So it looks something like this. 0.75 is 1 minus 0.75. Yeah, or you could just put 0.25 if you wanted. 1 minus 0.75 is 0.25. Okay, all over 1,000. Hit enter. 0.0136. Alright, and now let's do the second part. It says check that the 10% condition is met. Okay, so here we have 1,000 people as our sample size. Okay, so what would our population size have to be? At least 10 times more than this. So ask yourself, are there at least 10,000 young adult internet users between ages 18 to 29 in the world? Would that make sense? And we would say yes. Clearly, there are more than 10,000 young adult internet users. Okay. So that's how we would respond to the 10% or the independence condition. In part C, it says, is the sampling distribution of p hat approximately normal? Check that the large counts condition is met. That's these two things. Okay. So let's check that. I'll just do that on a piece of paper. So to do the large counts condition, we need to make sure n times row is greater than or equal to 10, and the word and is important, and n times 1 minus row is greater than or equal to 10. Well, our n is 1,000, and our row is 0.75. So if I work that out, 75% of 1,000 is 750. 750 is greater than 10. And if we do the other part of that condition, 1 minus row, well, row is 0.75, so 1 minus 0.75 is 0.25, and that would be 250. And that's also greater than or equal to 10. So we're good. The large counts condition is satisfied. Okay. Basically, these two numbers will add back up to n. Okay, they have to. All right. So I would say, because the large counts condition is satisfied, and sometimes, guys, this large counts condition, it's called the normal condition. You'll see why here in a second. Because the large counts condition is satisfied, the sampling distribution of p hat is approximately normal. It's important to use that word approximately. Okay. In every inference test, you're going to perform, for proportions, you're going to perform a large counts condition. Okay. Likewise, in every inference test that we do in confidence interval, you're going to have to perform some sort of independence condition check, okay, where the sample size or the population size is at least 10 times greater than the sample size. Those checks have to be performed. Now let's look at the next part of this question. It says, if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? Okay, so in one case we have a sample size of 1,000, and in another case we have a sampling size of 9,000. Okay. So what did we say before? Okay. We said that mu of p hat equaled rho equal 0.75. Okay. That wouldn't change here. Okay. The true proportion is still 0.75. What would change, however, is the spread of the sampling distribution. Now, we kind of call this something else. We have some common nomenclature for it. Some people refer to this as the standard error, okay, instead of standard deviation, because it's a standard deviation of a sampling distribution. So a quick way just to call it what it is standard error. Okay. All right. Well, before we've got 0.75 times 0.25 over 1,000. But over here, this became, or this would become 0.75 times 0.25. But since the sample size is now 9,000, that denominator is bigger by a factor of 9. Let's see what that, and we said that this before equaled 0.0136, sorry. It's a rough estimate for it. Okay. Let's not put this into our calculator. Let's just think about this. And I'll try to explain why there's an easier way to do this. Hopefully you agree that 9,000 is the same thing as 1,000 times 9. Okay. And now we can rewrite this as 0.75 times 0.25 over 1,000 times another radical, which would simply be 1 over 9. Okay. Well, we already know what that's equivalent to. That's the same thing as this over here. Okay, so that's going to equal about 0.0136. However, what's the square root of 1? It's 1. And what's the square root of 9? It's 3. So if we increase our sample size by a factor of 9, okay, you're actually decreasing the standard error by a factor of 3. Why? Because a 9 is actually underneath a square root, and the square root of 9 is 3. And since it's in the denominator, it's going to only make it a third. So in effect, that's the same thing as taking this previous number and dividing it by 3. Okay, so if you understand that, the calculation becomes real quick. You just take the previous number that you got. Okay, actually, let's just hit divided by, oops. Let's say answer divided by 3. Okay. So 0.0046. And that should make sense from a theoretical standpoint. Okay. The bigger our sample size is, okay, if this was what it was before, that's what the distribution looked like before, the new distribution would be much more condensed. Okay, the spread would be less. They would be closer to each other. The values would be closer to each other. So the spread is a third less. All right. We're almost done with section 7.2. There's one more part. It says using the normal approximation for p hat. Okay, so we can use the normal approximation as long as the large counts condition is satisfied. Again, that large counts condition is sometimes referred to as the normal condition for proportions. And it says, inference about a population proportion rho is based on the sampling distribution of p hat. As long as the large counts condition is satisfied, the sampling distribution of p hat, this thing right here, okay, or this thing right here, is approximately normal. So what they're saying is that as long as this large counts condition is satisfied, if I were to plot all those p hats, it would look like a normal curve. That's what that's saying. In that case, we can use a normal distribution to calculate the probability of obtaining a simple random sample in which p hat lies in a specified interval of values. So remember, the height of these values along the normal curve are for different values of p hat in repeated samples. Okay. Now it says, suppose that 35% of all first-year students attend college within 50 miles of home. Okay. So that's some sort of proportion or percentage. So what it told me is that rho equals 35%, which is 0.35. Okay. Now let's do part A here. I think there's only a part A. Yeah, there is. It says find the probability that a random sample of 1,500 students will give a result within 2 percentage points of this true value. That's another way to verify that it said true value. That means the true proportion. It says show your work. So what are we really looking for? We want to know the probability, that's when I'm going to use a capital P, that a certain sample proportion is going to fall between 2 points of this value, either on the high side or the low side. So what's the chance that I would get a sample proportion of between 33% and 37%? See, that's within 2 of that, that's within 2 of that. So on our sampling distribution, this graph represents the sampling distribution of p hat. Okay. So all these values on the x-axis are p hats. And everything up here refers to a frequency, or a relative frequency. All right. So we know that the mu of p hat, the mean of the sample proportions, is going to equal rho, which equals 0.35. So that's the value that's going to fall right in the middle. Okay. That's going to fall right in the middle. Since that's rho, it's going to be the same thing as the mean of the sampling distribution. What I want to do is I want to figure out what's the probability that any given p hat falls between 0.33 and 0.37. So in other words, I want to find the area of this normal curve. That's what I'm looking for. Okay. Now, I drew a normal curve here, but I didn't check that to make sure I was allowed to. So before we can actually do calculations here, we should check the large counts condition. We should check the large counts condition. And we should also check the 10% condition as well. We really should check both of these. Okay, and there's really one more condition to check, and that's the random check. So let's start with the random because that's easy. Did the problem tell me that I had a random sample? Yes. So simple random sample stated in problem. Okay, so that works out. The 10% condition, you have n equals 1,500 here, 1,500 students are in your sample. So what's 10 times that? It would be 15,000. Okay, so in the US, are there at least 15,000 first-year college students? Yes. So I would say clearly there are more than 15,000 first-year college students. It didn't even talk about US, it just talked about college students. Okay, clearly there are more than 15,000 first-year college students all over. Okay, so that condition checked out, this condition checked out. Okay, so we also have to do a large counts condition. So we have to make sure that n times rho is greater than 10 and n times 1 minus rho is also greater than 10. Okay, so our n is 1500, our rho is 0.35, and if we go ahead and plug that into a calculator, we find out that that's 525, and that number is bigger than 10. So that part checked out. And the next part, if this is 525, if we actually plug in these numbers, 1500 times 0.65, that's what that would go in that parenthesis. 1 minus 0.35 is 0.65. It would turn out to be 975. And that number is also bigger than 10. Okay. How did I figure that out so quick? Because this number plus this number have to add back up to 1500. Okay, so all three conditions are met. Okay, so this one lets me use a normal curve. Okay, this next one, what does the 10% condition allow me to do? It allows me to figure out what sigma of p hat is by using that formula. So that would be the 0.35 times the 0.65 over the 1500. Let's figure out what that is on the calculator. I'll do 0.35 times 0.65 over 1500. Okay, 0.0123. Now let me just store this answer in letter A. So that's 0.0123. So what do I know about this distribution? It's normal with a mean of 0.35 with a standard deviation of 0.0123. Why is that important? Because I can use my calculator to now figure out that, to figure out this area. Okay, so in the calculator, I'll go normal CDF command. Okay, so if I go normal CDF, how do I get there? I hit second, then the vars button because it says distributions above. I would choose option 2 for normal CDF. Okay, the lower boundary is 0.33. That's where this comes in. The upper boundary is 0.37. The mean of this distribution is 0.35. And the standard deviation is that value that I stored in for alpha. So by storing it, I don't have to worry about compound rounding. I hit paste. And I hit enter. So this answer, which is what I'm really after, was 0.896. And doing all that work for one answer. Okay. Let's write a quick sentence to explain the answer. There is an 89.6% chance that we would observe a sample proportion. Okay, we would observe a certain p hat between 0.33 and 0.37. So there's an 89, almost a 90% chance that we would get a p hat in between those two values. And there's only 10% of p hats that would fall outside of those values based on this number. So that's the meaning of the answer. All right. That's a good place to stop because that's the end of the examples for 7.2. Hope the explanations helped y'all.